So you're wondering why twin and single engines are so different. Here's something shocking. Twin engine owners might grin as they pull away from the marina thinking twice the engines, twice the power, and twice the speed. Well, not really. Behind that smile might be hiding twice the cost, half the efficiency, and a big hole in their wallet. But wait, there's more to this story. The twist is that engine configuration fundamentally transforms everything about your boat's physics. From fuel consumption to emergency handling, it's not just about counting propellers. It's about understanding how these radically different setups change your boat's entire personality, capabilities, and even the psychology of how you'll handle risk on the water. Here's where physics gets fascinating. Twin engines give you something called differential thrust. One run forward, one reverse, and your boat pivots without moving forward or backward. With engines typically spaced 3 to 8 feet apart on recreational boats, you're creating opposing forces that generate pure rotational movement. A well-handled twin can spin 360 degrees in little more than its own length. The spacing between engines acts as a lever arm. Wider spacing means more turning force, just like using a longer wrench gives you more torque. Catamarans with engines in separate hulls, sometimes 20 feet apart, demonstrate this principle dramatically. They can hold position in wind and current that would send a single-engine boat sliding sideways. But here's what changes at planing speeds. Single engines often deliver superior handling. That single propeller creates one coherent thrust stream, one predictable force vector. A single-engine boat typically runs its prop directly in the center of the transom, creating a stable steering axis. The outboard skeg sits directly in this high-velocity water stream, maintaining steering effectiveness even at low speeds. Twin setups introduce complexity at speed. Counter-rotating props, standard on most twins to cancel torque effects, create opposing helical water flows. These spiral patterns can interfere with each other, particularly in the zone between the engines. When props are too close, some builders space them just 18 inches apart to maximize interior room. The turbulent interaction can reduce thrust efficiency by 8 to 12%, according to naval architecture studies. If you're finding these engineering insights valuable, hit that subscribe button now, because we're about to reveal why your twin-engine friend might be burning 30% more fuel than necessary, and the upcoming section on something called synchronization loss will completely change how you think about twin-engine efficiency. Let's address a fundamental misconception. Doubling your engines doesn't double your speed. Hull speed follows the Froude number calculation. Speed increases with the square root of waterline length for displacement hulls. And for planing hulls, resistance increases exponentially with velocity. Adding power gives diminishing returns. Two 250 horsepower engines won't push you twice as fast as one 250 HP engine. You'll gain perhaps 25 to 35% in top speed. Acceleration tells a different story. Two props biting into undisturbed water means more immediate thrust and reduced cavitation. Think about it. Each prop on a twin setup handles half the load, operating in its optimal efficiency range. A single large prop trying to transmit 500 horsepower might cavitate violently during hole shot, while two props sharing that load huck up instantly. The propeller diameter difference matters enormously. Single-engine installations typically run props 17 to 24 inches in diameter. Twins use 14 to 18-inch props. Smaller props have less rotational inertia. They spin up faster, responding more quickly to throttle changes. This creates that snappy sports car feel twin boats are known for. Everyone assumes twin engines equal twice the safety. The reality is more nuanced. Yes, if one engine experiences catastrophic mechanical failure, you have another, but according to Boat US claims data, complete engine failure represents less than 3% of propulsion-related insurance claims. The majority involve fuel contamination, electrical problems, or cooling system blockages, issues that often affect both engines simultaneously since they share fuel tanks and similar environmental exposure. When you lose one engine on a twin setup, you don't necessarily get a free ride home and may need some skills to slip into your berth. The off-center thrust creates what naval architects call a turning moment. The boat wants to pivot around the working engine. In calm conditions, you can compensate with good captaining. In 6-foot seas with 20-knot winds, you might be fighting the helm constantly, exhausting yourself while making minimal progress. However, twins provide system redundancy beyond propulsion. Dual charging systems mean electrical failure isn't catastrophic. Two cooling systems mean overheating one engine doesn't end your day. Modern twins often feature crossover fuel systems, allowing either engine to draw from either tank, providing flexibility if contamination affects one tank. Twin engines fundamentally alter your boat's physics. The concept called mass moment of inertia determines how easily your boat rotates around its vertical axis. Weight distributed wider from centerline increases this moment, making the boat more stable directionally but slower to turn. It's why a bowling ball is harder to spin than a basketball of the same weight. This distribution affects seakeeping dramatically. In following seas, where waves approach from behind, the wider engine spacing helps prevent broaching, that terrifying sideways spin that can lead to capsizing. Offshore fishing vessels often choose twins partially for this stability enhancement, not just for redundancy. Yet, twin installations typically add 600 to 1,200 pounds versus a comparable single, and this weight sits far aft. Many twin setups require bracket extensions or modified transoms, shifting the center of gravity backward. This creates stern squat at speed, increasing wetted surface and fuel consumption. Some boats require extensive trim tab use just to maintain proper running attitude. Here's where the numbers get revealing. The longitudinal center of gravity, LCG, on a typical 30-foot boat should sit at approximately 35 to 45% of waterline length from the transom. Twin engines can shift this aft by as much as 8%, dramatically affecting performance. For every inch the LCG moves aft, you need approximately 2 degrees more trim angle to maintain plane, and each degree of trim increases fuel consumption by roughly 3%. The vertical center of gravity, VCG, also changes with engine configuration. Outboard twins sit higher than stern drives, which sit higher than inboards. A pair of 600-pound outboards mounted on a bracket raises the VCG by approximately 4 inches compared to a single inboard of equivalent power. This seemingly small difference reduces the boat's righting moment by up to 12%, meaning it heels more in turns and feels less stable in beam seas. Consider the gyroscopic effects too. Spinning propellers create gyroscopic forces that resist changes in orientation. A single large diameter prop spinning at 4,005 RPM generates significant gyroscopic stability, helping the boat track straight. Twin smaller props generate less individual gyroscopic force, and when counter-rotating, they cancel each other's stabilizing effect. This is why some twin-engine boats feel looser or less directionally stable at speed, requiring more frequent steering corrections to maintain course. Still tracking with me? Perfect, because the fuel consumption revelations coming up include a technique called economy cruise mode that many twin-engine manufacturers don't even mention in their owner's manuals. Subscribe and ring that notification bell so you don't miss our next deep dive into marine systems that could save you thousands. Here's the hard truth about fuel consumption. Twin engines generally burn 20 to 30% more fuel than a single engine producing equivalent speeds. This isn't simply double consumption, it's worse due to additional factors. Each engine operates at a less efficient point on its power curve. Propeller efficiency decreases due to smaller diameter and increased underwater appendages. Two lower units, struts, or shafts create parasitic drag. Real-world example. A Grady White 330 Express with twin Yamaha 250s burns approximately 42 gallons per hour at 30 knots cruise. The same hull with a single Yamaha 425 burns roughly 28 gallons per hour at identical speed. That's 50% more fuel consumption for just 17% more total horsepower. But experienced twin owners employ single-engine cruise mode for extended range. Shutting down one engine and running the other at optimal RPM can achieve better economy than a comparable single. The key is alternating engines every few hours to balance wear. Some long-range cruisers plan entire voyages around this technique, using both engines only when fighting currents or making port. The break-specific fuel consumption (BSFC) curves tell the complete story. Marine engines achieve peak efficiency at approximately 75 to 80% load. A single 400 horsepower engine running at 300 horsepower operates near this sweet spot, achieving perhaps 0.45 pounds of fuel per horsepower hour. Two 200 horsepower engines producing the same 300 total horsepower each run at only 37% load, where BSFC deteriorates to 0.55 or worse. That's a 20% efficiency penalty before considering any other factors. The cube law relationship between speed and power consumption creates interesting optimization opportunities. Reducing speed by just 10% can cut fuel consumption by 25 to 30%. On twins, this effect is magnified because you can drop below the threshold where both engines are needed. Many trawler yachts with twin engines cruise on one engine at 7 knots, burning 4 gallons per hour, but need both engines to reach 9 knots while burning 12 gallons per hour. That extra 2 knots triples fuel consumption. Propeller slip percentages reveal another efficiency gap. A properly loaded single prop operates at 10 to 15% slip at cruise. Twin props, being smaller and often spinning faster to achieve the same boat speed, typically show 15 to 20% slip. This represents pure inefficiency. The props are spinning faster than theoretical speed, wasting energy churning water rather than creating thrust. Some boats improve twin-engine efficiency dramatically by installing larger, slower-turning props, though this sacrifices some of the acceleration advantages twins typically provide. The financial impact extends far beyond purchase price. Maintenance costs effectively double: 2 sets of filters, zincs, impellers, and thermostats. Annual service for twin 300 HP outboards runs approximately $3,000 to $4,000, versus $1,500 to $2,000 for a single 400 horsepower engine. Over a decade, maintenance alone creates a $15,000 to $25,000 difference. Insurance premiums reflect increased replacement costs and complexity. Twin-engine vessels typically cost 8 to 12% more to insure, though this varies by insurer and region. Haul-out costs increase with twin installations due to additional running gear inspection and bottom paint around extra appendages. Surprisingly, twin engines don't always cost more initially. A single Suzuki 350 outboard retails around $32,000, while 2 Suzuki 200s total approximately $34,000. The premium is modest considering the redundancy gained. However, replacement parts for twins must be kept in matched pairs for many components, doubling inventory costs. There's a hidden cost nobody mentions at boat shows. Depreciation curves differ significantly between configurations. According to BUC research and NADA Guides data, twin-engine boats typically depreciate 2 to 3% faster annually than comparable singles. Why? The perceived maintenance burden scares off second-hand buyers. A 5-year-old boat with twin 250s might be worth $8,000 less than the same model with a single 400, despite costing more initially. This accelerated depreciation particularly affects the 3rd through 7th years of ownership, when buyers become wary of impending major service requirements. Consider slip fees too. Twin outboards often require wider slips due to engine spacing and bracket width. Marina slip pricing typically jumps at every 2-foot increment of beam. A boat requiring a 12-foot slip versus a 10-foot slip might pay an additional $1,500 to $3,000 annually, depending on location. Over 10 years, that's another $15,000 to $30,000 in ownership costs that never appears on the purchase agreement. The parts availability issue becomes critical as engines age. Common wear items for popular single engines remain available for decades. A water pump impeller for a 20-year-old Volvo Penta 5.7 costs about $60 and ships overnight, but matching twin engines from a smaller production run, you might wait weeks for parts, paying premium prices. Some twin owners stockpile critical spares, tying up thousands in inventory. One owner of twin 2008 Mercruiser 496s told me he keeps $4,000 in spare parts aboard because certain components are backordered for months. Winter storage adds another dimension. Twin stern drives or inboards require double the antifreeze, double the fogging oil, and double the labor for winterization. In northern climates, professional winterization runs $400 to $600 for a single stern drive, versus $700 to $1,000 for twins. That's another $3,000 to $4,000 over a decade of ownership that rarely factors into purchase decisions. Optimal engine spacing involves complex calculations. The ideal center-to-center distance typically equals 20 to 30% of beam width, balancing maneuverability against efficiency. Too narrow causes propeller interference, too wide requires excessive bracket width or compromises hull design. Engine synchronization becomes critical for comfort and efficiency. Unsynchronized engines create harmonic vibrations that fatigue both crew and components. Modern electronic controls provide automatic synchronization, but mechanical systems require constant adjustment. Even 1 RPM difference at cruise creates an annoying beat frequency. Toe angle. The slight inward angles of drives or shafts must be precisely set on twins. Incorrect toe causes the boat to crab sideways, increasing drag substantially. Singles self-center naturally, but twins require careful alignment to track straight without constant steering input. The mathematics of optimal spacing get complex quickly. The wake field from each propeller expands at approximately 15 degrees from the shaft centerline. To avoid interference, the wake field shouldn't overlap until they're at least 3 prop diameters downstream. For typical 15-inch props on 4-foot centers, the wakes merge about 6 feet behind the transom, but if those same engines were on 6-foot centers, the wakes wouldn't merge until 9 feet back, maintaining cleaner water flow and better efficiency. Steering geometry changes dramatically with twins. The turning radius equals the boat length divided by the sine of the maximum steering angle, multiplied by a factor related to engine spacing. Wider-spaced engines can achieve the same turning radius with less steering angle. A 30-foot boat with engines on 5-foot centers needs only 20 degrees of steering lock to match the turning radius of 3-foot centers at 30 degrees. That's a significant reduction in rudder drag during maneuvers. Modern digital synchronization systems use sophisticated algorithms to maintain harmony. Mercury's shadow mode technology allows one helm to control both engines with independent throttle and shift for each, automatically synchronizing RPMs within 1%. Yamaha's Helm Master EX goes further, using GPS and gyroscopic sensors to hold position within 2 feet even in 15-knot winds. These systems cost $15,000 to $25,000, but transform twin-engine handling from an art to a science. The propeller phase angle, the rotational relationship between props, affects vibration patterns. Ideally, props should be timed so blade positions mirror each other, cancelling certain harmonic frequencies. Some high-performance boats spend thousands of dollars on dynamic balancing and phase timing to eliminate vibrations that would otherwise limit speed or cause structural fatigue. It's the difference between a smooth-running machine and one that shakes your teeth loose at certain RPMs. Neither configuration claims absolute superiority, each excels in specific applications. Singles dominate where simplicity, efficiency, and cost matter most. Bay boats, bass boats, and coastal cruisers. Their mechanical simplicity means fewer failure points and easier troubleshooting when issues arise. Twins shine for offshore sport fishing, commercial operations, and luxury yachts where low-speed control and redundancy justify complexity. The ability to hold position while fighting fish or maneuvering in tight quarters provides tangible operational advantages. Consider your actual use patterns. If 90% of your boating happens within towing distance of port in protected waters, twin redundancy offers minimal practical benefit. If you're running to distant fishing grounds or island hopping the Caribbean, that second engine provides invaluable peace of mind. Let me give you some real-world scenarios that illuminate the decision. Tournament fishing boats almost universally run twins, not for speed, but for positioning. When you're backing down on a marlin doing 40 knots, the ability to steer with engines while the rudders are essentially useless in reverse becomes worth any efficiency penalty. Professional captains report that twin-engine boats land 20 to 30% more billfish due to superior boat handling during the critical final moments of the fight. Commercial operators face different calculations. A charter fishing boat running 200 days annually might burn an extra $15,000 in fuel with twins. But one saved trip due to engine failure covers that difference. The Coast Guard commercial vessel regulations actually favor twins for certain passenger operations, offering reduced inspection requirements for vessels with propulsion redundancy. This can save thousands annually in regulatory compliance costs. Geographic considerations matter enormously. In the Pacific Northwest, with its strong currents and rocky shores, singles dominate the recreational fleet. One engine failure in those conditions often means immediate anchoring anyway. The current overpowers a twin boat's single-engine capability, but in the Gulf of Mexico, where you might be 70 miles from shore over relatively calm water, that second engine could mean the difference between a tow bill and motoring home. The resale market tells its own story. According to yacht broker statistics, twin-engine boats over 35 feet sell approximately 23 days faster than comparable singles. Buyers perceive twins as more capable, even if they'll never use that capability. It's the marine equivalent of buying a four-wheel drive vehicle for suburban commuting. The capability provides psychological comfort worth quantifying. Singles dominate the under 25-foot market, where purchase price sensitivity peaks and operational simplicity matters most. Consider crew requirements too. Singles can be effectively single-handed in most conditions. Twins, particularly in challenging docking situations, benefit tremendously from a skilled crew member handling the second throttle. Many husband-wife cruising teams specifically choose singles to avoid the two-captain problem that twins can create during stressful docking maneuvers. If you've absorbed all this technical knowledge, you're clearly committed to becoming a more informed captain. This understanding separates weekend boaters from serious mariners who make decisions based on physics and facts, not marketing hype. So here's your action plan. Smash that subscribe button immediately, because next week we're exposing why those expensive joystick docking systems might actually be making you a worse boat handler. Plus, I'll reveal the old-school docking technique that works on any boat and costs nothing to master. Drop a comment sharing your engine configuration and your biggest surprise from today's deep dive. Are you reconsidering your next boat setup? What's your most memorable engine-related experience on the water? The most insightful comment gets featured in our next video. Until then, keep your props clean and your fuel filtered. This is your source for marine knowledge that goes beyond the surface. Subscribe now, and I'll see you on the water.